I'm Katie Williams, and I'm going to present our work on data abstractions and mental models of data. To begin, I'm going to describe a fable about elephants and explain how that connects to mental models of data. So, this fable, which has roots in Hinduism and Jainism, describes five people who are unable to see who are encountering an elephant for the first time. Each person touches a different part of the elephant and comes to a different conclusion about it. For example, the person who feels the tusk says the elephant is hard and smooth like a spear, and the one who feels the side thinks it's like a wall. Each person has a different mental model of the elephant. When you're collaborating on a data set, each person may have a different mental model of the data, shaped by their prior knowledge, expectations, and inferences. This mental model impacts their preferred choice of data abstraction, or how they see the elephant. Problems can arise when the abstraction used in the visualization doesn't match the user's mental model. So for a quick overview, a data abstraction is a generalizable framework for a data set. For example, you might have a specific data set about food and the nutritional breakdown for that food. This specific data set can be abstracted to a tabular data abstraction. As a visualization designer, I know how to work with tables and I know my design options when dealing with tabular data. However, there are data sets that could have multiple abstractions that fit the data. So with the food table example, I might find visualizing groups of food to be more useful for how I want to use the visualization. Here I have a group of fruits and a group of vegetables, and to see these connections, a grouped data abstraction would be more helpful. As visualization designers, we typically receive our data set and select the data abstraction based solely on the data. But how do you know that the data abstraction matches your viewer's mental model? What if it doesn't match and the system is harder to use than it could be? Our prior work in data abstractions shows that there is flexibility in the choice of data abstraction and that this choice has far reaching implications on the visualization and on the user. So, what if we started with no data abstraction, not even a table? To tackle these questions, we conducted a study about mental models and data abstractions. We conducted semi structured interviews where participants sketched their mental model of a dataset. We recruited 28 participants from our university's computer science Discord server and undergraduate computer science mailing list, as well as posting flyers and word of mouth in the local YMCA community. Of the participants, 20 had computer science related work background and 8 had other occupations. Participants ranged in age from 18 to 77 years old, with the mean age being about 31. During each semi-structured interview, rather than presenting participants with tabular data, which has been shown to influence design choices, we presented participants with one of 3 data sets in paragraph form. On the next slide is a data set. For those of you who like to participate, please pause the video and begin drawing the data set. You have 2 folders. In the first folder are 2 text files and 3 images. In the second folder are 4 text files, 2 code files, and 1 folder. In this folder are 1 text file and 1 image. I'll also show you the other 2 datasets we used. Here's our junk drawer dataset with a mix of quantities of pencils, pens, and containers to group items. And here's our power station dataset, which could allow for edges between power stations and the recipients, but there's also quantities of recipients. So going back to the sketchers of the file system dataset, did you draw something similar to the file viewer on your computer? Or did you think of the files and folders as nodes and edges, aka you drew lines connecting pieces? Did you draw a large folder with the files inside of it, or did you do something else? Here are 4 of the file system dataset drawings. We saw a diversity of data representations and data abstractions from our participants. As an example, the following 2 drawings both use the same data abstraction, a hierarchy, but they chose slightly different data representations. Participant 6 here used icons and lines to show the relationships, whereas participant 24 deliberately chose text because they wanted the nodes to be clearly understood. In these next 2 slides, these participants used a totally different abstraction for the file system dataset. They used sets or grouping to show the data. Both participants used containment, or putting rectangles inside of rectangles to show the file folder contents. This participant actually gave us 2 abstractions in 1 image. They initially drew a hierarchy as a tree on the left, and then a bonus image on the right, they drew sets of rectangles nested within each other. We observed a wide variety of mental models, data abstractions, and depictions from the same dataset, as well as how these concepts are influenced by communication and purpose seeking. So, to analyze our results, we took an inductive thematic analysis approach. During data collection, three authors individually noted codes and thoughts regarding the transcripts and sketches, initially following an unconstrained open coding practice. These codes were recorded as memos on a shared GitHub repository to facilitate our remote collaboration and to track the provenance of codes. As these discussions took place, we moved to axial coding to develop hierarchical concepts. We used Google Jamboards to cluster and merge and split our initial codes and to identify concepts arising from multiple codes. We arrived at 24 consensus codes, which fall into three clusters of themes: mental model content, mental model elicitation, and mental model formation, as well as a secondary theme regarding beliefs about data. For the time, I'll highlight a set of codes under mental model formation. These codes relate to purpose seeking, and they surprised us the most. The rest of the themes and codes are in our paper. So, our purpose seeking codes are participants added or assumed tasks, participants suggested data sources, and participants desired to add data or information. And I'll explain those. So one participant who wanted to add a task, they had the power station data set, and they wanted to calculate the power station that produced the most power. So on the bottom image here, they wrote a bonus visualization about how they would calculate power production. Another participant who had the power station data set suggested a data source. They suggested that the data set is probably a municipal guide or a power company's guide to how to distribute power. As an example of adding information, one participant who had the junk drawer data set assumed this list would be used for an inventory, and they added a cost attribute to each item, since they knew items like stamps were more valuable than items like rubber bands. We recognized that the majority of our participants had a computing background. While not part of our original experiment design, we revisited our codes to check if any were heavily computing biased in their evidence. Again, I leave the details to the paper, but one code that solely had computing participant evidence was our node link sketched representations. All 9 node link sketches were done by computing participants. Now I'll show you all of the sketches for each dataset. What is significant about these sketches and relevant for visualization design and the design methodology is that there can be more than one data abstraction that works for a given dataset, and that preferred data abstraction can vary from person to person. As visualization designers, we need to experiment with how we elicit people about how they think about their data during the early stages of the design study process. I leave you with just 2 of our implications for the visualization community. The rest are in the paper. The first is beware of data abstraction elephants. Even in the file system case, where most participants cited a familiar source of inspiration, participants sketched a variety of concepts and imparted differing grouping biases. These realities present hazards in choosing effective data abstractions. We suggest that designers sample multiple target users, potentially multiple times, so that our interpretation of our users' mental models can solidify. Once solid, we can better identify what data abstractions best align with these mental models. Second, visualization design starts with data design. Many of our participants imagined beyond the data set. They suggested possible sources of the data, invented tasks to be done with the data, and wished for additional data or information. This curiosity may be due to the participants having no relationship to the dataset, but it could also be due to their inherent curiosity. This creativity can be useful to visualization designers as it highlights what aspect of the data the user finds relevant and the tasks and operations that the user wishes to execute. We visualization designers have a chance to be part of the data design phase if no real data is available yet. By being present in these discussions about data, designers can better understand the priorities and motivations of their users. Thank you for listening.